Okay, in this video I'm going to walk through my solutions for the practice exam number 3. In problem 1 we were told that we have an 11 kilogram block that's being pulled 7 meters across a frictionless surface by means of a rope, and the tension in the rope is 40 newtons and the work that's being done is 247 joules. So one of the big things that I like to do anytime that I complete a word problem is to write down the given information. So we have mass, distance, force, and work. Now work, remember, is just the measure of energy transferred to or from an object. So in general, we would say that the formula for work is force times distance, but you have to keep in mind too that the distance that you travel has to be in the same direction that the force is being applied. So in the event that the force is not being applied in the direction of travel, as we often see with this block style problem, if we're actually applying a force upward, yet we're trying to make the block travel forward, we have to compute the projection of that force down to the direction of travel, and we do that with this cosine multiplication. So fortunately for us, lots of the information was given, and the final question was, what angle does the rope make with the ground? So that really does imply that we're dealing with a problem just like we described here, and our job is to find the theta value. So before I substitute any numbers in, I'll go ahead and solve for theta. I've divided both sides by f and d, and then I applied the cosine inverse to both sides of the equation. And so now cosine inverse of our work, 247, divided by our force times distance. My calculator was originally set to radians, and this is the result that I got. We tend not to want radians in this format. Radians would be appropriate for rotational angles, but for angles, between two straight lines, let's go ahead and report that in degrees. And when I switched to degree mode, I ended up with 28 degrees as a result. And that does appear to be an option on the multiple choices. Now, keeping in mind with the notion of work being force times distance, we've got problem number 2, where an object is being acted upon by a force, and we have this graph to represent how much force is being applied over the distance that the object's being traveled. So if we think on the grand scheme of things, we've got a force measurement and distance measurement, and we can find the force that's being applied at any distance that the object has traveled. And so we want to know what the work was done by this force as it moves from 0 to 6 meters. Now, for us, we would like to simply multiply force times distance, but force is not constant. You can see how force is increasing for a while, and then it finally remains constant. If it was perfectly flat this whole time, and we multiplied our force, which let's say was 10, times the distance that was traveled, let's say 6, well, that force times distance, another way to think of that, is the area represented by the rectangle, whose height is 10 and the distance is 6. We don't have that here, so we're going to calculate the area underneath this curve anyway. And if you were in a calculus class and you knew the function that described this curve, we can use an integral of the force measurement with respect to distance. But since we don't have the function, and this is not a calculus-based class, we'll just find the area under that curve using traditional methods. Now that's a trapezoid, so the area formula for a trapezoid is half of the sum of the two bases times their height. You essentially have to find the average of the two bases and then multiply that by the height. So in this case, we have a base that's 6 units wide on the bottom, 2 units wide on the top, whose height is 10. And when I perform that multiplication, I end up with 40, which does appear to be an option in our multiple choice. For number 3, we've got a half of a kilogram football kicked from ground level. Now that may not look like a number, but that's good for us to note that the beginning height of the object is 0. There's an initial speed of 22 meters per second and an angle of 35 degrees. The ball follows a projectile path for 1.6 seconds before returning to the ground. Now here again, returning to the ground, that's an indicator that the height at the end, our final height, is also 0. So when we start at 0 and end at 0, the work done by gravity, or in other words, the energy transferred by gravity, not by the force of, impacting the ball or anything, but gravity itself, well, that work is going to be 0. And there are a couple ways to think about it. Most commonly, we think of gravity being a force that's associated with potential energy. And so a lot of times we'll say that the work done by gravity is equal to the force of gravity. We sometimes label that just as G, but bear with me here. The force of gravity times the distance that the object travels times cosine of 0. Now I'm saying cosine 0 because an object with respect to gravity is moving either up or down. So in this case, if we're moving up for a portion, we have negative work, and if we're moving down for a portion of time, we end up having positive work. Now this projectile path, if you recall from earlier units, is parabolic in nature, and if it starts at 0 and ends at 0 height, then it actually increases in height the exact same amount that it decreases in height. So I got a little bit ahead of myself here, and I might even end up saying instead of 0 degrees all the time, let's go ahead and call that theta, because sometimes it will be 180 degrees if we're doing work upward. Now all of that goes to say that in actuality, in this particular problem, this cosine computation makes no difference, because the distance that the object travels with regards to work here ends up being 0. The displacement from starting position to ending position with regards to the vertical direction or the direction of work is 0, and any force times 0 will end up equaling 0. Now in blue, I've kind of written one form of the definition of work due to gravity. From that we derive this alternate form that I've used here in red, where mg represents the force due to gravity, that's mass times the gravitational constant, and the distance that an object travels is its initial height minus its final height. And of course, by using that form, when the initial height was 0 and the final height was 0, there is our displacement of 0 multiplied by the other values, still ends up 0. No work is being done by gravity, at least when considering the entire event. There was work being done on the way up, and there's work being done on the way down, but the negative work on the way up and the positive work on the way down summed or netted to 0. Now in number 4, we're being told that a 5 kilogram mass is hung from a spring, and the spring stretched by 7 centimeters. What is the spring constant? So an assumption that's being made here is that the spring has stretched and then kind of come to rest. It's at its, I don't want to say equilibrium, because that's where the spring would rest in its relaxed state, but it's come to rest. The object has stopped moving. And what we should recognize here is that a spring that would, let me switch pens here, that would normally, at rest be, say, this length, is now being stretched to an additional length because there is some mass hanging on it. Now that mass has a downward force due to gravity, and we've listed that here in this free body diagram. And the spring has a force as well upward because it wants to constrict or return back to its equilibrium state upward. Now, since the spring is at rest here, it's the mass of the object has extended that spring and come to rest, then we can assume that these two forces are now equal and balanced. There's no other motion involved. So I've come to say that the force of the spring is equal to the force due to weight, and the force of weight is magnitude times gravity. The force in the spring, using Hooke's law, is K times X. Now we were told what X was, we were told what M was. Our job then is to solve for K, the spring constant, and if we took mg divided by X, that will isolate our K value, and when substituting the numbers in, we end up with 700 newtons per meter. And that appears to be a good choice on our list. For number 5, we have a 500-gram block pressed against a horizontal spring that has a spring constant of 180 newtons per meter. And the block gets compressed by 3.5 centimeters from its equilibrium point. If the block is released and the horizontal surface is frictionless, that's good to know. How fast will the block be traveling when it leaves the spring? So we have a mass, a spring constant, and the distance that the spring is compressed. And by the way, I forgot to reiterate that here. This x value is a displacement. It's the distance that the spring gets displaced. But we have all that information, and hopefully you're recognizing that the potential energy of the spring after it's compressed is being transferred into kinetic energy, and it doesn't appear to be there to be any energy loss or transfer outside of this system. So we can then go on to say that the potential energy of the spring is precisely equal to the kinetic energy of the block after it starts to move. So with potential energy of the spring described this way, 1/2 K times X squared, where X is the compression distance of the spring, that must be equal to 1/2 mv squared, mass times velocity squared, when the block starts to move. Now I had a couple students make this mistake in homework this past week. If you've got 1/2 on each side of the equation, you can think of moving this 1/2 to the other side by either dividing by 1/2 or multiplying by 2. But in any event, the result by having both of those numbers on the same or on opposite sides of the equation mean that they're going to cancel. Now if our job is to isolate v, I would divide by m and take a square root. So here's the generic formula or explicit formula for velocity in this case. When we make our substitutions, we end up seeing that the block will be moving at 0.66 meters per second, and 0.66 meters per second is 66 centimeters per second. So I'll go ahead and stop the video here, and that covers the first page, and I'll pick up with the next round of questions in the next video. Thanks for watching.